Jeremy Blum is a prolific inventor who has designed everything from prosthetic hands and structure climbing robots to 3D printers and home automation systems. His book, Exploring Arduino, along with his blogs and popular YouTube channel, has been used by millions worldwide to learn about electrical engineering and embedded software design. In 2013, Jeremy joined the Google X team where he served as the lead electrical engineer for various projects including Google Glass. In 2017, he was named on the Forbes 30 Under 30 list. Jeremy is currently the Director of Hardware at Shaper, where he is using computer vision to reinvent the way people use power tools. Ladies and gentlemen, please welcome Jeremy Blum.
Hi everyone, how's everyone doing? Great. I know it's after lunch, but that was extremely lame. How is everyone doing? Great. Okay, thank you. I'm on like literally zero sleep, so if I can have energy for the next hour, so can all of you. So I'm going to do my best to work my way through this. Hopefully I don't collapse up on stage, but I'm feeling pretty good. So. As mentioned, my name's Jeremy. I'm the Director of Engineering at a company called Shaper. We make handheld robotic power tools. Today, I will be speaking about, this is not on. There we go. Today, I'll be speaking about holistic product design. So at Altium Live last year in San Diego, I gave a talk about design thinking and the importance of empathy in product design, a concept that engineers don't normally think about a lot. And this talk is designed to expand on that in a way. I want to emphasize the importance of building a holistic view of a product, specifically for electrical engineers, and why it's important to have a holistic understanding of your entire product, not just the electrical components therein, in order to make a high quality, maintainable, debuggable, beautiful product. So let's first define what I mean when I say holistic. In the philosophical definition, holistic means something that is characterized by comprehension of parts of something as intimately interconnected and explicable only as reference to the whole. And what I mean by this, and this may seem obvious at the surface level, is that the electronics that you all in this room work on are part of a larger system. I doubt any of you are just designing products that are bare PCBs. You're probably designing them as part of a larger system. And understanding the other elements that go into that system is an important part of making the electronics function better, making them more testable, making them debuggable, making them work better, and meet your product goals. So first thing I'm going to talk about is problem oversimplification and how focusing too narrowly on a problem can cause you to miss things that are only visible by looking at the larger picture. Then we'll put this in the context of a larger system-level design and talk about how you design PCBs as part of an understanding of the broader system. And then finally, we'll kind of bring those together into what I call DFH, Design for Humans, or Design for Humans, and how you document systems in a way that's effective and helps reduce problems. So let's first talk about problem oversimplification. So engineers are really good at simplifying problems, and that makes sense. We want to make problems simple enough so that we can grasp them and do the math on the back of a napkin. We're often taught about how to design things in very ideal circumstances. So as an analogy, university mechanical engineering students, when asked to compute the aerodynamics of a cow, for example, will approximate that cow as a sphere. Very poor cow. So while this is great for learning fundamental concepts, it eliminates the corner cases from the problem definition, and sometimes that's OK. But it can also result in unforeseen irregularities that can make the problem harder to solve. So how many of you have ever looked at a problem or looked at a board that you've designed or a product you've worked on, and you look at something and you say, that should be working. I don't understand why that's not working. Everything says that should be working. Show of hands. OK. And you're pulling your hair out. And how many times has that issue arose because something in your design process, you made some assumption that something would work a certain way, something would operate under ideal conditions, and it turned out that maybe the conditions that you're operating in are not as ideal as you thought, and some environmental factor, some other factor that you didn't initially consider would have an impact on the design of the system, ended up having a large impact on that system. So the important thing here, though, is finding the right balance. It might not always make sense to approximate the cow as a sphere, but it also might not make sense to consider every conceivable second, third, and fourth order problem that might arise, because then maybe you're spending too much upfront time. So as engineers, we tend to look at a problem like this and design around these parameters when it actually looks like this. A lot more complicated. So sometimes that sphere approximation is good, sometimes it isn't. So how do we strike that right balance? Let's go back to an electrical example. So that was a mechanical analogy of sorts. In the electrical world, we can talk about a literal black box. So in this black box scenario, we have a simple business card size PCB. It's in a metal box. There's no connectors. Basically, the ideal scenario that we talk about when we're looking at, for example, a manufacturer of an IC data sheet, these are pretty much the parameters that they're assuming when they talk about how that chip is being designed. And I see Rick laughing, because that's the thing. You never trust the manufacturer data sheet, because they probably, or the application note, sorry, because they probably are not considering that chip's application in a completed actual product, which this is not. I would love, 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 love to design a product that looks and operates like this. I never will, and I doubt any of you will either. The reality is that modern products are not like that. So these are two products that I've worked on that was mentioned earlier, products that I've done electrical engineering work on. On the left is Google Glass Enterprise Edition. This thing has no room for heat dissipation. It has a dynamic, flexible hinge that's sending camera and display signals over it. It lives right next to a person's head. It has to pass all the EMC requirements. It requires hours of battery life, and it needs to have a wireless uplink. Origin, the product I work on now at Shaper, is the first ever power tool that I'm aware of that has a quad-core processor in it and a computer vision system packaged inside. And it needs to operate in a high static environment. It needs to pass the superset of EMC regulations that would apply to both a telecommunications device and a 26,000 RPM spindle motor. Those are not easy things to accomplish, especially if we were to consider either of these as a set of black box electronics. So quick detour to explain what the hell Shaper Origin is, for those of you who don't know. Shaper Origin is a handheld rotary cutting tool, a robotic handheld power tool, that basically uses computer vision to augment your abilities as a human to cut something. You load in a digital design file. You do the coarse movements. The tool compensates for your movements in real time and keeps you on track on your design. So if I want to cut a perfectly straight line and I'm moving like this, I'm exaggerating, but if I'm moving like this, the tool's spindle is moving in the exact opposite direction at the same speed to ensure that the resulting cut path is perfectly straight, giving you a machine quality cut with a handheld power tool. So I'll show a quick video of some of our customers using this tool, because I'm going to continue using Origin as an example of a holistically designed product from an electrical engineering perspective. So it's useful to have this context. And just because I'm really proud of it, and it's a really cool tool that people do really cool stuff with. So this product has taught me a lot about predicting issues before they happen, and developing an electronic design process that allows us, Shaper, to move quickly as a company. When we announced Origin at the end of 2016, saying we would ship it in a year, we did that. Unlike many other crowd-funded hardware products, we delivered on time in a tight timeline with a very complicated product. And our ability to do that was made possible largely by the things that I'll continue to discuss through the rest of this presentation. So as of January of this year, Shaper has been acquired by TTS, which is parent company to Festool, a German company. How many of you have heard of Festool? Show of hands. OK. Great. It's a different answer that I get when I'm in the US, because their presence is not as large in the US. But we're really proud to be part of that family now. And we've actually already been working with them for years because they designed or co-designed the spindle motor that sits inside of Origin with us before that acquisition happened. So they bring decades of experience building really great power tools, and we bring experience with computer vision and software systems. So, okay, we agree that designing PCBs is complicated. The simplified versions that we might use don't always address all the corner cases that we might encounter in the real world. So let's talk about designing them as part of a larger system. How do we know what trade-offs to make? What are the job functions that are tangential to us as electrical engineers, and how do those impact the decisions that we make as electrical engineers or PCB designers? So for me, I kind of started to learn about the importance of these tangential roles that surrounded me in my engineering position when I was at Google. But this didn't completely happen to me until I was at Shaper, the 6th or 7th employee at the company. This was about 4 years ago now. And the reality was just, it wasn't that I had to learn how to work with software engineers or the people responsible for our manufacturing test or our factory fixtures or the people responsible for understanding how we were going to sell this to end customers. Those people didn't exist. So I was doing them, or my other 5 or 6 coworkers were doing them. And so I've done everything from manage our Twitter account to writing our product manual, literally wiring Ethernet through our assembly factory. I've been exposed to all these things that are not generally in the job description of an electrical engineer. And in doing so, have learned quite a bit, I think, about how those roles are important, and understanding those roles are important to doing a better job in the electrical engineering design of a product. So many of the people in this room presumably work for much larger companies than Shaper. Maybe some of you work for a startup, or you do contract work for a larger company. And I think you might be surprised by what you can learn from how a smaller company addresses some of these holistic product design principles, which is what I'm going to talk about. So in the keynote I gave last year about design thinking, I used a similar diagram to what I'm going to show now. And I basically said, pick a couple of other things that are tangentially related to your role as an electrical engineer or a PCB designer, and start to learn them and understand them. And this is important in that it allows you to get a sense of what the people around you, what their requirements are in a product. And they're often, I'm sure, well, let's do another show of hands here. How many of you have ever had conflicting requirements in a product with other types of engineers on your team? Yeah, OK. This is all about compromise, right? And compromise works best when you can understand the perspective of the other person. So here's an example of some of the things that you might hear from the people around you. The industrial designer might say, hey, that metal box, that perfect rectangular metal box, actually it has to be half plastic. The mechanical designer might say, this product has to survive sawdust. The person in charge of your factory programming fixtures might say, we have to be able to calibrate that system effectively. The person responsible for your end customer story and how you're going to market this product says it needs to work seamlessly with, in our case, ShaperHub, which is our cloud infrastructure. OK, so this thing needs to have wireless connectivity. Cool. The person responsible for design for manufacture, design for test, design for assembly would say, we want to 100% test all the sub-assemblies so that when they get to final assembly, we already know that they're guaranteed to work. The person in charge of UI and UX design might say it needs to be beautiful and intuitive. Your embedded software team is going to say, we need to be able to debug this as we go. And when we get return units back from the field, we need to be able to get into them and understand what went wrong. And your quality assurance people want to be able to measure the performance of the tool or whatever product it is that you're making and understanding if it's working the way that you're marketing to your customers that it should be working. So when I talk about PCBs in context, what I'm really talking about is understanding these roles that exist around you. And by the way, everyone else in your company has a similar diagram with them at the center of it. And it might be your job as someone who understands the holistic design process better than they might to encourage other people in your company to get an understanding of all these things that go around your job role so that they can have a better relationship with those people and understand their needs and requirements. So some companies that I've interacted with over the years or have spoken to people who work at those companies, without naming any names, some companies explicitly prevent this kind of collaboration where you try to learn more about the embedded software design of your product, or you want to better understand what the mechanical engineer is doing, and actively spending some of your time not trying to become a mechanical engineer, but just understanding how they approach the problem. Maybe you learn some CAD tools, or you want to spend some time in the mechanical manufacturing facility where they're die casting some of your parts, so you understand that process and how it might impact the whole product design down the line. Some companies might prevent this because they think people will work most efficiently if they have narrowly, specifically defined roles. You focus on that role, and the person next to you will focus on their role, and maybe there's a program manager or something that coordinates all those things. Well, some degree of specialization is good. I will give them that. However, I would make the argument that it can be detrimental to overall product design if these people are not speaking effectively. I'm not saying they have to do each other's jobs. They just need to speak effectively. So what happens is when people over-focus, when they have this one-track mind, this tunnel vision, is they crisscross, and they end up in different places. And what happens is a year later, you end up with a product where the electrical engineer met his requirements for the product, the mechanical engineer met his requirements for the product, but guess what? Those two products are not compatible with each other, and now you can't ship this product. And so I call this tunnel vision, and basically is you're getting so focused on your specific end goal that you're not considering the product as a whole. So maybe you're thinking, it's not my responsibility. That's what the program manager is for, the product manager is for, to make sure all these different disparate needs stay on track, and that may be true to an extent. But I would posit to you that while you may have the best product manager or program manager in the world, they might not understand how a change in electrical architecture that you might make now could impact the way your factory fixtures are going to function 12 months from now. That's not in their job purview. They want to keep people on track, meeting deliverables, meeting timelines, and they may be very good at that. But you as an electrical engineer or a PCB designer should understand the roles around you and how the changes that you make are going to impact those roles. So the way we do that is by designing beyond the PCB. So when I say designing beyond the PCB, I mean that you have to touch and understand the things around you and integrate that into your design process for your electronics that you're working on. So I'll give a couple of examples from the tangential job roles that I mentioned in that previous chart. So the first one is going to be obvious, or at least it should be obvious, which is you need to directly communicate with the people around you on that chart. Don't rely on a middleman to do it for you. You need to communicate and understand directly what they're working on and what their needs are so that you can design or solutions to problems that are compatible with their solutions to the problem. This means making the effort to work with them directly, sometimes literally sitting right next to them. And for those of you who don't have the luxury of being able to sit right next to that person, it means using the tools at your disposal to be able to exchange design information effectively. So little plug for Altium here. The 3D design capabilities in Altium, the multi-board capabilities I use religiously with our mechanical design team to pass data back and forth, and it helps them validate my designs and vice versa and make sure that they're actually going to be compatible with each other. Another important part of this process, I believe, is not saying you have to become a mechanical engineer, but understanding the things that impact their design process is incredibly useful. So this means a couple things. On one end of the spectrum, it can mean learning basic 3D CAD if you're not already familiar with some platform for doing that. I like to use Fusion 360 for modeling parts that I then import into Altium. Just gives me a sense of kind of what their workflow looks like, even if I'm not doing the mainline mechanical engineering design of the whole product. It gives me a sense of what they go through in designing something. The other part of that is understanding the processes and tolerances that impact them. So that means understanding when they say, we're going to extrude this part, or we're going to cast this part, or we're going to 3D print this part, or we're going to injection mold this part. What does that mean? What are the tolerances on those things? How does that impact your ability to design electronics that are going to necessarily need to interface with those mechanical systems? The next thing that I'll use as an example is understanding the needs of the software team. So I'm biased here because I also manage the embedded software team at Shaper. But I do believe that our ability to make a tightly integrated product is predicated on the communication between our hardware and software team. So show of hands, how many of you work on products where software eventually gets loaded onto something that you've made? OK. Actually, better question. Does anyone not? OK, I didn't think so. No one, right? Yeah, OK. So how many of you would say you're comfortable writing some software? OK, it's a pretty good show. All right, that's great. So I'm not saying that you need to be writing the end production software that necessarily runs in your hardware. Maybe you are. Maybe that's part of your job description as we kind of see a lot of these things meshing together more and more. And that's great. If you're not, what I would advocate is, and I think this kind of accomplishes two tasks in one, is get more involved in the test and bring up procedures for your electronics. In our case at Shaper, what I mean by that is we design most of our own factory test fixtures, all the things that do the final assembly tests of our sub-assemblies and the full product. And what we do for that is a lot of those tests are relatively simple. We're taking basic measurements, things like that. And so we have this platform that I've put together called Shaperduino that we use internally, Plan Arduino, where we basically use the Arduino software infrastructure system, load it onto custom test electronics. And it makes it really easy for our electrical engineers, and I can now say plural electrical engineers because we finally have another electrical engineer at Shaper, which is very exciting. It makes it easy for our electrical engineers to develop test software that is testing the electronics that they are also designing. And by designing the testers for your electronics, you are necessarily going to make testable electronics because you're responsible for both parts of that system. And so this kind of goes back to that holistic design principle of kind of understanding how all these things connect together. So using this software platform, we do an array of automatic subassembly testers that we put together that are based on these electronics and Arduino-based software that's kind of quick for us to spin up. But in many circumstances, I've found, and you've probably found too, that I don't necessarily have the bandwidth to design the electronics for the mainline product and also design the factory test fixtures and do the mechanics for the factory test fixtures. As much as I might find those things interesting, there's just not enough time in the day. So this comes back, again, to understand the mechanical side of things a bit, getting a little bit more exposed to that, and using even some of the basic 3D modeling and assembly capabilities of Altium's multi-board feature I now use. I'll bring in solid bodies for parts of a fixture, communicating with my fixture vendor or my final assembly site or my SMT site that might be using this fixture, bring that in, generate a rough 3D model. This is a rough 3D model of how my boards need to mount in there in order to function correctly. And then I ship this off to whatever vendor on whatever continent is making the final fixture. And I say, here's what it needs to look like. Here's how these things need to connect together. I haven't done the full mechanical design, but I know enough about the mechanical design to make sure it's going to work the first time. Another example from that puzzle diagram is the customer story. So this is something that I believe in particular is underserved on the engineering side in a lot of organizations. And that's really understanding what is the end purpose of the product that you're working on. Often as engineers, we're given a set of requirements. Product needs to do X, Y, and Z. Maybe this product is being delivered to end customers like our product is. Maybe it's for internal use at your company, or it's for a limited subset of people in the world. But they have some set of requirements that product needs to meet. And you get those as technical requirements. You know, this product needs to run on 24 volts. This product needs to operate for this amount of time, whatever it is. And if you don't understand the customer stories that went into developing those requirements, then it's harder for you to make intelligent decisions about how to execute on those. So I'll give you an example from Shaper again, which is this is one of our customers. He does professional flooring inlays. And this is him using Shaper on, I think this is still probably one of our largest projects to date. Someone recently did like a 40-foot conference table, so that might have beat this. But the general idea here is our marketing team, I say team, but it's basically one person, went out to some of our prospective customers, tried to understand from them what are the ways you want to use our product? What are some of the things you want to do today that a product does not exist for allowing you to do. And this is a project that this guy wanted to do for years and simply had no feasible way of executing it. He has now done it with Origin. But this kind of customer requirement about wanting to do a large working space, in this case it's indoors, but potentially also working outdoors, having to work on the floor, not necessarily on a work table, these are all things that fed back to me. They might not normally feed back to an electrical engineer, but I heard directly not just about the technical requirements that these marketing or customer stories researchers believed were dictated by the customer stories, but the customer stories themselves. How do they want to use the tool? And so that feeds into making decisions that impact the electrical architecture. How do we position the handles in a reasonable way so that they're ergonomic when they're on the floor versus when you're on the table? Might seem like a mechanical problem, also has an impact on the wiring and the electrical harnesses. How do we tilt the screen so that it's at a reasonable angle for using it on the floor, or using it outside in high glare has an impact on how we source that screen, how bright it is. These are all things that then feed back to how much power does this unit need to have, how much brightness does the backlight need to have. So these are all things that come back to me. And if I had just been told the thing needs to have a 5-inch screen, the thing needs to have handles, we might not have developed a product that allowed people to work in these sorts of situations. So if you listen to that feedback, it enables you to build the electronics in a way that you're going to end up with a better end product for your customers. And in case it's not really clear from looking at this photo, these are all individual inlaid pieces of wood. So the elements are cut out into the floor. He cuts out matching elements, and they slot in perfectly. And another part of the customer story, I don't know how well this phrase translates. It's a popular Silicon Valley phrase that I kind of cringe to say, but it captures it well, which is eating your own dog food. Does that translate at all to German? Not really. But maybe you get the idea. If you're a dog food company and you're making dog food, eat your own dog food. Understand if it's good or not yourself before you start selling it to your customer, in that case, dogs, in our case, woodworkers. And so I use the product a lot. All of the people at Shaper use the product a lot. This is me installing a wireless charger in my nightstand a couple months ago. On the floor, a use case that was empowered by having a better initial understanding of customer stories, because I live in a very small apartment. And just a couple of Easter eggs in this photo. You'll see my book being used as a stand to hold this thing up. I didn't cut through the book. You'll also see Happy Holden's book on my bookshelf in the background, which I got from Altium Live last year. And the bookshelf is made with Origin also, by the way. OK, so we've talked about the context that your PCBs lived in. We've talked about how you understand that context to design beyond the PCB, understand the mechanical requirements and how they work, understand the software needs, understand the customer stories, a couple examples. Design for humans is about taking that information and putting it into making meaningful documentation packages. And I think that making good documentation is something that is very infrequently discussed, but is extremely important and has the potential to save you generally an enormous amount of time and an enormous amount of money if you do it correctly. And so I use features like Altium's Draftsman and StackUp Drawings, and I used some of the 3D design capabilities as part of making my documentation packages that I output. But this is about taking that information and then making sure you deliver it to your manufacturers, is one example, as a way of holding them accountable, making sure that they make the things that you want them to make, and that if they don't, you can point at the documentation and say, no, it was supposed to be this way, and it's clear. So when I say design for humans or documentation for humans, I'm really talking about 4 types of humans. The first one is you, as the designer, the electrical engineer, the PCB layout artist, what have you. So let's do another show of hands question. How many of you have made a design decision, picked a value for a component or laid out something in a certain way, made sense when you're doing it, and then a year later you're looking at that product, it came back to you, there's something wrong with it, or something went awry, and you look at it and you're like, why did I do it that way? Like, I know I had a reason at the time, but I cannot for the life of me remember why I chose to do it that way. OK, Follow-up question, how many of you have learned from that experience and then documented those things better the next time so you don't make that same mistake? OK, very honest crowd. I appreciate that. So not all the hands went up that went out the first time. So what you should take away from this presentation is use that as a learning experience, document that thing the next time, and over-document, especially to yourself. Because when we're designing something the first time around, it's always clear as day to us. And then we do 17 other projects over the course of the next 6 months. And all of that information gets archived way in the back of our brain. And you're lucky if you can retrieve it. And maybe some of you have better memory than I do. But I struggle with that particular issue quite a bit. So the first part of Design for Humans is designing for yourself. That means putting the right documentation on your schematics and your layout and your Draftsman files, what have you, that are going to enable you to come back to that design. And anything that is not extremely obvious is made obvious by your own documentation and notes. I promise this will save you countless hours of time, and it's so easy to do. The second humans that you're designing for are your customers. Again, whether these customers are consumers out in the world or there are other people inside of your company that's going to be designing or consuming this product in some way, it's important for them to have a good experience with your product, presumably. Presumably that's something that's important to you. And if your product malfunctions in some way, suppose it's overheating, is there a mechanism in this product that allows the product to diagnose itself and to understand what is wrong and to be able to surface that error or problem in a meaningful way to customers so that that information can feed back to you and you can address the problem? That's part of the Design for Humans process. The third group is your peers. So there's an old adage that says if you give a man a fish, he'll eat for a day. If you teach a man to fish, he'll eat for a lifetime. Same thing goes with your peers. They are fishermen trying to fish, and the lures are the documentation that you're giving them. And if you integrate meaningful documentation into your schematics, and this should be happening automatically as part of addressing the first one. If you're designing well for you and documenting well for you, you should be documenting well for your peers also. It's almost no additional work. It's maybe a little bit more context that they would need in order to look at a schematic and say, OK, that's why that value was chosen. Or maybe for a software engineer to say, OK, this is the GPIO port that I'm using, and here's why I need to set its drive strength to this value, whatever. For your mechanical engineers, it might mean documenting the thermal properties of a certain part of your design and giving that information to them early so that they can incorporate that into their thermal modeling of the product. The last group is your manufacturers. So they're also human, contrary to popular belief sometimes. There's a tendency to treat manufacturers like they are the machines that they operate. They are humans. But we think of them as input-output machines, right? If we give them the right input, they will produce the same output every time. Has that always been everyone's experience? No, yeah, OK, I didn't think so. However, if you give them enough documentation, I would even go so far as to say over-document, certainly as opposed to under-document. You're giving them the tools they need to succeed and succeed repeatedly and reliably. And this is particularly important if you're ever working on a design where you think this might go to another manufacturer at some point. So let's dive into each of these with some examples. So designing for humans, designing for you. I mentioned this is about making reasonable notes to yourself, making it stupidly easy for you to understand what you were thinking when you did something. This is a very simple example. This is an excerpt from a board that we use in our factory as part of an automated assembly process. It just needs to drive a stepper motor. Really, really simple. When I was designing it, I knew I only had enough time to do one spin of the board before we were going to hit our manufacturing deadline and needed to start using it in the factory to build stuff. And we weren't sure exactly how we were going to use this yet. The software wasn't written yet. I didn't know what micro-stepping mode I wanted to drive the stepper motor in. For those of you who are not familiar with stepper motors, it's basically how many clicks you get driven from the stepper motor driver as it does its rotation. And you're trading off torque for the number of ticks that you get around. And so I made a reasonable guess. I defaulted it to 1/8 micro-stepping. But I put in solder jumpers, so you can see that documented in the schematic here, but also on the board down the bottom here. and made it easy for me, if I need to, if I end up being wrong, we didn't have enough GPIOs to drive these stepper mode select pins directly. They need to be hard set on the board. I could cut those and resolder them and adjust them. And since I knew I was going to be on the ground at the factory doing this, and for those of you who have spent time in a factory, maybe you don't always have the best internet connection. Maybe you can't connect to your VPN and get your design files. I've had every number of things go wrong there. I just put the information I needed right on the silk screen. This is a factory board. I don't care how much information I put on here. And so if I need to modify it, I ended up not needing to modify it. But if I did need to modify it, all I had to do was look at this and cut the right jumpers and adjust things accordingly. And so that was a documentation process for myself that had the potential to save me considerable time and very, very valuable time in this instance, because we were on a short time crunch. And this board was required as part of the assembly process of our product. And if I didn't have this documentation, the ability to change it, then we might not have hit certain timelines, and time is money when it comes to manufacturing. Next example is designing for your customers. So I mentioned earlier about understanding the environment that your customers are going to operate in and making smart design decisions early. In our case, there's a couple things for us to consider. On the left, you'll see some of our testing for dust incursion into the tool and how the tool survives a situation like that. It does, spoiler. And the other thing is how we handle error states. So I briefly mentioned earlier building in the functionality into your product so that it can self-diagnose to the greatest extent possible. And there are trade-offs here in terms of cost, in terms of complexity, and you have to make those trade-offs. But when feasible, if you have the sensors that enable it and we can give useful and meaningful feedback to our very human operators to help them take corrective action in a way that they ideally, in our case, don't have to call customer support, but it's very clear what happened. So in the case of Origin, it has a certain corrective range. If you move it out of the range, it retracts. But it tells you and it explains why it retracts. And there's many other error states for different ways you can conceivably cause an issue. And we populate that information up to the user, and we have the sensors built into the electronics to capture that information and display it in a meaningful way. And even if, from a cost perspective, it doesn't necessarily make sense to include those things in the end product, it doesn't mean you can't include them in the prototyping phases and use it to understand what the potential failure modes are. Next one is your peers. So this is a quote from one of my coworkers that I'm very proud of. And I make very, very verbose schematics. I mentioned earlier I've made enough mistakes or had enough problems where I look at a schematic a year later and I don't remember why I did something or why I picked that resistor value. So I document all of it, like a lot. And I put in all the information that's required for an embedded software engineer working on, let's say I have a board with a microcontroller on it, to understand how they need to set up that chip. Which IOs need to be inputs versus outputs, which ones need to have a certain drive strength. Do we anticipate needing to have spread spectrum driving on this clock line for noise reasons? All that information goes in there, and then they can parse that information out themselves and look at the documentation themselves and make decisions, ideally, in my world, without having to come over and ask me those questions. It's useful to collaborate with the people around you, but it's also nice when you can allow them to fend for themselves with the information that you've generated as part of your documentation. And if you do that, you'll save yourself time, you'll save them time, and you'll help them meet their puzzle chart where they are at the center by helping them to better understand the electrical design of the product and why you made the decisions you made. And then the last one, coming back to it, is your manufacturers. So in the case of your manufacturers, writing good documentation and requirements early is going to save you more time later. Judy describes this to me as slowing down to speed up, taking more time earlier on in the design process to document things properly so that later in the design process, you are not running into problems because there was a miscommunication of things. And so this comes in many forms. In my case, I do use the Draftsman functionality in Altium quite heavily. I use the stack-up functionality. By the way, for the Altium folks in the room, I have some feedback for ways the stack-up can be farther improved in the Draftsman drawing, but it's really good where it is right now. And communicating that information to your, in this case, fabricator early, communicating with them about what the stack-up's going to be early, and being pedantic in how you call things out. So like, for example, when I'm defining my outer copper, I'll say, not just the finished copper, not just the foil copper, but I expect it to be this thickness of original foil and this amount of plated. And I get that information and coordinate that information with the fabricator first and make sure we're in agreement on that. And then that information is what goes into the build documentation. A really important part of that for me is not allowing them to change things that don't get reflected in the documentation. And this is a thing that is really tempting to not do properly because it takes a lot of time. So classic example, you send a design off to a fabricator. They say, hey, some of these traces, we can't make that thin, or we can't handle this spacing, or based on the dielectric we're using, we need to change the width and spacing of these controlled impedance lines, for example. And they can say, hey, we'll just change that in the Gerbers for you. And you can say, yeah, do that. And they will happily do it. And you'll be on your merry way, and those boards will come out, and they'll work great. And then 3 years from now, you'll no longer be working at that company. Someone else will have inherited that design, will need to take it to a different fabricator, send the files off. That fabricator will not tell them that those things need to change for the design to be met correctly, for example, the impedance control. And now, none of your controlled impedance traces are actually controlled impedance anymore. And you have no idea why, because the boards that were previously being built were being done so not against your saved documentation for that product, but by modifications that you had allowed them to make on the fly. And so again, this is about striking the right balance. You have to find the right balance of time, and sometimes there's urgent things that you need to change, and you can say change that. But if you do that, you have to go back to your documentation and reflect that in your documentation and save that in whatever system your company is using to save that documentation as the exact representation of what's being fabricated. And this gives you flexibility in the event that you have to move manufacturers or add a second supplier or something like that, making sure that your fabricated data actually matches what you designed in, and not allowing your fabricator to just change it on their own. Another part of this is how you design and document your testing systems for your manufacturers. Do you just say, hey, here's this board, it's got these voltage rails, make sure they're at this value, have a good time? Or are you more explicit about, I need you to test this, this, and this things, they need to be in this error range, I need you to be able to push this data to our server or save the logs to us in some capacity, track it against the serial number. There's a big difference between just saying, functionally test this board, and saying, here's how you need to functionally test this board. And that involves writing additional documentation. Sometimes it means designing that functional tester yourself if this is a board that's sophisticated enough to require functional testing. Because not that you can't trust your manufacturer to do it, but again, going back to something we discussed earlier, if you are co-designing the electronics and the things that test those electronics, you're going to necessarily make testable electronics, and you're going to necessarily make a tester that can test those electronics effectively. As opposed to doing this feedback loop process with your manufacturer where you make a board, you say test this, 3 months later they're like, hey, we're ready to test this board, but you don't have the right test points on there for us to do these things. And then you end up saying, fine, I waive those tests because you're already behind deadline, and now you're shipping that board without the proper testing, and it fails in the field or something. So this is about giving your manufacturer the documentation and the tools that they need. So the example in this slide is a functional tester for our vision assembly. As they assemble the camera to our vision board with our illumination LEDs and our flex, they pop it in here. It runs a series of tests automatically, and it uploads the results. And importantly, it gives feedback to the manufacturers, and there's a document that goes along with this that says, here's all the conceivable ways this can fail. If you see this failure mode, here's what you do to rework it and to fix that problem. And this puts more accountability on the manufacturer. It gives them the tools they need to succeed. And it improves your yields because instead of just throwing out the devices that don't pass because they don't understand what the hell is happening, they have a set of procedures that they can use to make those boards pass, and ship those functional boards to you. Don't underestimate the importance of pretty pictures. Even if you're using MS Paint, a picture is worth 1,000 words, and sending an image describing how you want something to be set up is infinitely better than doing it in an email. Ideally, doing it in some sort of version-controlled document explaining how something is to be built is the best scenario. That information should go along with your release documentation for your fabrication and your assembly drawings. Say, here's how you fabricate it, here's how you assemble it, and now here's exactly how you test it, the things I expect to be tested, how I expect them to be tested, and if you're providing the tester, how to operate that tester. This also has a huge benefit of doing a really good job of overcoming language barriers. I'm sure a lot of you work with manufacturers whose first language is not the same as your first language. And no problem there. That's fine. I'm sure they're still really, really good at what they do. But the reality is that language communication issues happen, and pictures are really clear. So that's PCBs in context, using that information to design it beyond the PCB, and then pairing that with documentation that makes it easier for you to understand what you did, makes it easier for your peers to understand what you did, makes it easier for your manufacturers to implement what you did, and ensures happy end customers for your product because your product works the way it's supposed to, and because they get feedback and understand when the product is not working the way it's supposed to. So let's review. PCB and electronics design rules of thumb results from the simplification of complex problems. This is the black box problem that we talked about. Rules of thumb are great until they're not. And I'm sure that all of you have met situations where they are not. So when we oversimplify, when we exclusively follow rules of thumb without understanding the context in which those rules of thumb have to exist, we lose sight of the context that our electronics operate in. If you better understand the constraints that impact the other parts of the larger product, you will make better design decisions in the PCB that will increase its likelihood of performing the way you want it to. So this is all about understanding what are the requirements of the people around you, your end customers, the mechanical engineers, the software engineers, the UX designers who will eventually be pushing content onto this product, if it has a screen, for example, and making sure that you understand what problems that they're going to face so that you can help them face those problems effectively. Things that might be obvious to you at the time of implementation might not be obvious to you in a year and might never be obvious to your peers because they didn't design it. So if you put in the right information to both empower yourself and the people around you, you will save a ton of time. I guarantee it. It will require more upfront work. I guarantee you, over the long run, this will save you time. If you create that documentation that is tailored to be used by humans in a meaningful way, is not just the fastest thing that you can conceivably get out to a fabricator or an assembler, you will eliminate problems before they arise, and you will make your job easier in the future because it'll be easier to support the product. It'll be easier for people around you to get the information that they need. So how many of you want your job to be easier? OK, write good documentation. Done. You can pay me later. OK, so to wrap up now, I have to put in a few plugs at the end here, right? Yeah, 5 full minutes for plugs. So the first one is that Origin starts shipping in Europe very soon. I did not have room in my carry-on luggage to bring one with me, unfortunately. However, I will be in Stuttgart Friday and Saturday at Holzwerken Live, which any of you are welcome to attend. I'll be there with Origins from our Stuttgart contingent of Shaper, and we'll be demoing it there. If you want to get on the waiting list to be one of the first people to get Origin in Europe, this is not a pre-order. This is a waiting list. They'll be available in Europe very soon. You can follow that short link to sign up for that list, blum.fyi/origin-EU. And if you have questions about Origin or still don't understand what the heck it is, you can feel free to find me after, and I'm happy to explain it. Second plug is the second edition of my book just went to press like 2 days ago, so very good timing. You can pre-order it now on Amazon. It ships November 19th, I think. If one of the things in that slide deck that was interesting to you or you think might make sense for you to get better at is understanding the embedded software design that goes into a product that you might be working on, this book is pretty much aimed at this exact target audience. People who have experience with some type of engineering, but either want to learn a little bit more about the electrical side of things, you guys probably don't need that, as well as the embedded software design of products and writing embedded software for microcontrollers using the Arduino as a platform. The second edition of this book is over 100 pages longer than the first edition. It adds a whole lot of new stuff, Internet of Things, all those buzzwords. And if you want to know more about what Shaper Tools is doing or what I'm doing, you can Google me, find it all online. It's all up on the internet. And that is all I have. Thank you very much.